Okay, there you go. Thank you.
Hello, everybody. So I'm Francois Berenger. I'm a postdoc researcher at the University of Tokyo. And usually I do cheminformatics method development research. So for ligand-based method usually, but recently I do structure-based things also. So I'm in the laboratory of Professor Tsuda. And I'm not sure if you know this lab, so mostly they do material informatics, but I'm one of the few persons who do cheminformatics for small molecules. And so today I will talk about 3D sensitive encoding of pharmacophore features. If you are interested by this topic, so there is a paper published in ACS JCIM with the same name. So if you want to know more details, then you can read the full paper. And we have the same figures, but the paper has more explanation, of course. So there are some talks about chemical fingerprints in this meeting. So this is another chemical fingerprint, which is a 3D sensitive that I will describe. And it's a counted fingerprint, but it's a truncated one. So we have seen other fingerprints which were uncounted and folded. So it's another kind of fingerprint. So my presentation will follow this very basic outline. So I will give an introduction of the topic. I will try to explain the method. And then I will talk about the benchmark dataset I'm using, which is, I think, very important. And I will show many results. So first, what is a pharmacophore? So this is a PDB entry from RCSB called the 6QTL, so the PDB code. And it's a so-called caffeine recognizing antibody. And so this is a pharmacophore. You can see the pharmacophore are detected by the NGL viewer. So if you go in the ligand view, you go on the PDB page, maybe the ligand or 3D view, then ligand view, and you select NGL viewer, then you can have this kind of description. So here we have the caffeine molecule, and the position of the molecule is constrained by so 4 pharmacophore interaction. So there are 2 hydrogen bonds in blue, here and here, and there are 2 pi stacking interactions in dashed green. And those things are, it's internal to the protein, so it's not part of the pharmacophore. Here also there is a protein internal hydrogen bond, it's not part of the pharmacophore. So I have shown a pharmacophore, but in fact the pharmacophore is made of pharmacophore features or pharmacophore points, you can call them. So this is the same molecule, and I tried to highlight with a UCSF camera what are the pharmacophore features which are detected for this molecule. So in white, you can see the hydrophobic features. So there are 3 of them you can see, but in fact, the aromatic rings are also hydrophobic features, but you don't see because it's not true transparency, this drawing. And then there are 3 hydrogen bond acceptors with orange spheres. So this is for one molecule. And so this is an overview of the method I propose. So it's a whole encoding pipeline I describe here. And I call the method ACP4. So this is the name of the open source software. It means autocorrelation of pharmacophore features. So you need an input molecule or a 3D conformer. Then you use RDKit with a bunch of smart strings to detect the pharmacophore features in this molecule. So you get this molecule is transformed into this set of 3D points, and points are typed by a pharmacophore feature. And then you apply an autocorrelation function with a cutoff distance. So an autocorrelation function is it's a mathematical thing. It can transform a 3D object into being a rotation translation invariant. So if you know the atom pairs in RDKit, atom pairs use autocorrelation, but on the molecular graph, so the distance is a topological distance, and here I use a Cartesian distance. And the cutoff distance makes the fingerprint being truncated. So it has a maximum length. So it gives us a list of pairs of pharmacophore feature, and each pair has a pharmacophore type, distance in angstrom, and another pharmacophore type, pharmacophore feature point type. Then I use what I call a channel separation. So I think there are 21 channels to decode, to encode all the different pharmacophore feature pairs you can encounter. Then I use another technique called linear binning. So if you don't know linear binning, it's a kind of histogram, but it's a histogram which is resilient to some amount of noise when you discretize data. And then you need to concatenate all those vectors to get the final encoding for the whole molecule. And this is the kind of encoding you get. It's the actual one for caffeine. It was truncated because there are zeros on the left, on the right end that we don't care about. And so the channels are visualized here. If there is a vertical dashed line, it means we are at a channel boundary. And the first channel was aromatic to aromatic pair. And the second is hydrophobic to hydrophobic, etc. And then, so I use the dataset to benchmark the virtual screening performance, so to do similarity searches with this fingerprint. So it's a rather recent dataset, I think maybe 2 years old, from Didier Rognon team in Strasbourg. And you see, so there are like 15 protein targets. For each protein, I show you how many non-active molecules there are and how many inactives. And then you see the hit rate for each protein target. So the thing I like about this data set is that all molecules were assayed. So the actives and inactives, they come from Campbell. And the actives are true active, they have an IC50 value. And the inactives one were also assayed, and they don't have an IC50 value. So you see this data set is very hard. And if you are lucky, like one target has a 5% hit rate. So the random hit rate is 5%, but many other targets, they have a super low hit rate. And it's very hard to sometimes to work with this dataset. But I think it's realistic, maybe if you look at HTS campaigns and the hit rates they get, so maybe it's realistic. And so it's a medium size, maybe even a little large dataset. And you can use it to benchmark structure-based things, but also ligand-based things. So there are PDB structures inside, and you can do a docking and this kind of thing. So I compared my method versus several methods, and one of them is called Pharaoh. So Pharaoh is an open source software to work with pharmacophores. And they do optimal superposition of ligands in the pharmacophore space. So they do the 6-dimensional optimal superposition, which is it's costly computationally. And so I compared with them. So I take 50 random molecules which are active for a given protein target, and then I look what is the AUC, the work AUC we get with this query on this dataset. And I did this for all the proteins. So then I show if it's in bold, it means it's the best score for this line, and it's statistically significant according to Cohen-D statistics. If the protein target is in bold, it means Kolmogorov-Smirnov test says the two distributions are significantly different. So if it's bold, it's great, but I like to look when things don't work and how often. And you see that some targets, you get random screening performance, 0.5 AUC on average. This one is also kind of random performance, 0.49. 0.46 is maybe worse than random, and here also. So it doesn't always work, unfortunately. I compared also versus the RD-kit pharmacophore fingerprints. So the RD-kit pharmacophore fingerprints are for the molecular graph, I think, originally. But you can change the matrix, distance matrix parameter. So you can give a 3D distance matrix, and then the RD-kit pharmacophore fingerprint becomes a 3D sensitive. So I compared against it in the same experiment, I mean, same kind of experiment, and I used the same statistics, Kolmogorov Smirnov for a line, and to compare the two things, I also co-ND to check is the difference big enough. So also in this case, so it doesn't always work. Like RD-kit also can give a random result, even maybe worse than random here. So this kind of things. And okay, something else I wanted to know. So if you do a query with a bioactive conformer, does it work? So a bioactive conformer is like the ligand you found in the crystal structure. And the only way would be you don't have a conformer, but you have a conformer generator. So I use OpenEye Omega because we have an academic license for it. And I tried, so if you query with Omega, a generated conformer, or with a bioactive conformer, is there some significant difference? So over many targets, I did this. And so this is a frequency on the y-axis. On the x-axis, you have an AUC value, and less than 0.5 is needed. The greater compared to 0.5, the better. And I didn't see any difference. So the good thing is, well, if you have the bioactive conformer, you can use that. But if you don't have the bioactive conformer, then just generate the good low energy conformer, and you can run with this. So currently, the method, it comes in two flavors. So I call it the ligand comparison mode or the binding site comparison mode. And you see the method has only two parameters to compare ligands. So there is a delta X, which is a discretization parameter. So it's 0.5 angstrom for ligands, and the cutoff distance is 5 angstrom. And for binding sites, so you need an extra parameter. There are only 3 parameters then. So you still need the discretization parameter, which is bigger, 0.9 angstrom. And the cutoff distance is way bigger because you know the binding site is bigger than a ligand. I mean, the binding site sometimes englobes the whole ligand, so it's a bigger thing around the ligand. And the cutoff distance, so I use a ligand-defined binding site. So any protein atom within 5 angstrom from any ligand-heavy atom, I call this the binding site. So low number of parameters, you can feed them to optimize the performance in some data set or use the defaults, of course. It's a sparse encoding, so the fingerprint is mostly zeros. And for an example, ligand encoded, so there were only 50% non-zero values in the vector. For binding site example, there were only 18% non-zero values. So it's not very high dimensional. So for ligand, we have 232 floats. And for binding sites, we have 946 floats. But it's mostly zeros everywhere. So you can use a sparse encoding, I mean a sparse data structure to store those. So it can be very memory efficient. And so initially, I just wanted to compare ligands. But at some point, I realized that if we can do ligands, we can probably do other things. So then I tried to match binding sites. You can query with a binding site. And so I used the two data sets. So this is the work AUC curves. So the true positive rate versus the false positive rate. And the training set was a SCPDB, so a data set of ligandable protein binding sites. And on the training set, we got an AUC of 0.82. Then I tried on an external test set, which is Vertex data set from the literature. And we got an AUC of 0.84. So in terms of classification performance, I think it's quite strong, those AUC values. Okay, we compared the method with other binding site comparison methods because in the literature there are many binding site comparison methods. So they are named here. So Probis, Pocket Match, Kripo, etc. And this table is rank ordered by decreasing AUC. So the best method in terms of AUC is the first one, but you can see that it can only process 64% of the data set, so it will crash on the rest. And as a computer scientist, I don't like when software crashes on me. So this one pocket match is more robust. Only 0.6% of the data set is not processed, and Creepo not as good. But okay, in terms of the method which can work on the real data set, so there are only 3 methods. So ACP4 is one of those, with cytoline and fuzzcav. And in terms of performance, so I think the performance of a Creepo, cytoline, ACP4, and fuzzcav, it's statistically, it's not a significant difference. And okay, maybe method which perform a little bit less well is a Procare and Shaper. And so that's the binding site comparison benchmark. I like methods which screen fast also, because sometimes you have many molecules and you still want to process them. And I can use supercomputers, but I'm a lazy person. So if I don't have to, I prefer not to. Here I saw the y-axis is a screening frequency. So it's either molecules per second or binding sites per second. And there are 2 use cases. On the left square, it's for ligands queries. And on the right square, it's for binding site queries. So this is the FAO software, which is open source and written in C++. I think it's on GitHub, the code. So FAO can compare about 3,300 molecules per second, which is already, it's fast. I mean, for cheminformatics, it's acceptable. So ACP4, if it's the first time you screen a database with your query molecule, so you can screen 30,700 something molecules per second, but usually you prepare a database once, and then you will query it many times with different interesting molecules. So the second time, I mean the production run, when you screen a database, we can screen 374,000 something molecules per second. And this is a production run. This is what you will do most of the time. So for binding site, there is the same story. First time you screen a database, a binding site database with a query binding site. Maybe we screen like 2,500 something binding sites per second on a single core, no GPU, a single thread. And if we screen subsequent queries for the same database, we can screen like 132,000 binding sites per second. So I mean, it's fast enough for me. And okay, one thing I wanted to see as a cheminformatician, I was very interested by this kind of plot. So on the x-axis, you have a Tanimoto distance. So Tanimoto distance is 1 minus the Tanimoto square. And it's a proper metric, mathematically speaking. It's a true distance. So it can be exploited to accelerate things. And on the y-axis, there is an activity probability. So this plot, it answers the question. So on one protein target, one from this dataset, if you have a query molecule, how far can you go from your query molecule and still get active molecules with a reasonable hit rate? So the answer is, well, if you go over 0.6, let's say 0.7, Tanimoto distance from your query, then you get the random hit rate of the data, the chemical library you are screening. But if you take something more reasonable, like maybe you want molecules which are maximum 0.4 Tanimoto from your query molecule, then you see the hit rate can vary between 30% to maybe 100%. So this is an interesting range of distance queries. And okay, I do also some binding site similarity searches to look what are the top binding sites I guessed with a binding site query. So my queries were those 2 structures. So the 500 PDB using the caffeine binding site, and then another PDB, so 3FM, which has also a caffeine binding site. So CFF is a caffeine ligand code in the PDB. And then I look, so how far is the other binding site? And I put the Tanimoto distance on this arrow. And I can see, okay, the molecule inside the nearest binding site. So with this query, I can tell you, so this is a false positive, false positive, false positive, and this one is a true positive. So it can find in the very top hits, in the 5 top hits, you can find a caffeine, and you can find an analog of caffeine. And for this query binding site, this is a false positive. This is a true positive. I mean, it's not a caffeine analog, but when you look at the binding mode of this molecule, it's a superset of the binding mode of caffeine, and it's a protein from the same family. So it's also a ligand binding in the same binding site. And okay, I'm finished. So this is open source. It uses RDKit, and I'm really glad RDKit can handle smart strings. And I'm glad even another open source software, so Farmer, they have all those smart strings to identify the pharmacophore features. So it's very nice. And so we are on GitHub. You can go in ACP4, and this is the software. So this is a Fukusukeku. I think he's a good luck charm in Japan. So he says thank you for your attention. If you have some questions.
Okay, are there questions? I will come with the mic to you. Yes, okay. First up here.
Well, thank you for your presentation, was so illustrative. I have just 2 curiosities. When you say that you obtain similar results between the using the omega conformation and using the crystallographic structure, did you check in average or structure the RMSD between the omega conformation and the crystallographic structure?
Sorry, can you repeat the question?
Yeah, sorry. Did you show a graph and using the crystallographic structure as a reference and using the lowest energy conformer using omega? So did you check the RMSD between the 2 conformations using the crystallographic and the conformation obtaining by omega?
No. So I didn't check the distance between the lowest energy conformer generated by omega and the bioactive conformer. I didn't even check that.
It's just curiosity. And one more question. In average, how many conformers do you use for the virtual screening?
You mean to prepare a data set?
Yeah.
So in these experiments, I just generated 1 conformer per molecule.
Oh, wow, nice.
Good. Because the data set is already big. I mean, some targets have 300,000 molecules. So if you do a conformer enumeration, it becomes very big.
Wow, good results then. Thank you.
Yeah. You probably have to.
Yeah, I have 2 very short questions. But the first one is, did I understand it right that during the autocorrelation, this is rotation invariant, translation invariant, but also mirroring invariant or not? So can it basically separate a fully mirror situation or not?
Maybe what you mentioned is okay. When we apply autocorrelation, you lose the stereochemistry. So a molecule and its mirror image after autocorrelation, it becomes the same thing.
Oh yeah, okay, yeah. That was what I was wondering. And then the second thing is that I have done some like classic pharmacophores, and there definitely I can say you need lots of conformations if you want to get nice enrichment. Even if it needs to be done on scale of 100,000, usually it's worth the computational time to do that, in my opinion, at least.
Okay, good to know.
So this is my workout tonight. We do first crack and then afterwards.
So 2 quick ones. The first is, what are you using for the feature definitions? Because those are often key for the quality of your performance, of your pharmacophore performance. So for example, you use the RDKit pharmacophore fingerprint and the feature definitions there are not very good. I'm curious what you're using.
Okay, so for RDKit, I left the defaults for this pharmacophore fingerprint.
Yeah.
And to be honest, all software don't use the same pharmacophore definitions. So Pharao, I think they hard-coded the pharmacophore perception in their software. It's not using smart string. And some pharmacophore features are directional. The ones I use are not directional. So yeah, and as you said, so RDKit has a different pharmacophore feature definition. I didn't change, I use the default. And the ones I use are the pharmacophore feature smarts from Pharmer. So Pharmer is a published open source software for pharmacophore search.
Okay, thanks. The other thing is, I think anytime I see a comparison of two methods where you change your reference conformer and the results don't change very much. So when you compare bioactive conformer versus low energy conformer, that says to me that you have something probably 2D going on. So it would be interesting to see a comparison for your data of a 2D similarity measure. Something that's not 3D, something like a 2D pharmacophore even.
Okay, but yeah, maybe this result, there is a bias because the way I prepared the data set is by using omega already. So the conformers are omega generated. And then if you query with an omega generated conformer, then the performance is not different from the bioactive conformer. I mean, on average. And I guess omega is quite good at going near the bioactive conformer in many cases. So maybe that explains why it's good like this.
Yeah, I'm not sure I agree with that, but we can follow up on that later.
Yeah, thank you. So I had one question for slide 14. So
Thanks for
yeah, because two things about that. So because I mean, it's kind of the point of using pharmacophores, right? So that you even chemically very different compounds should also or are often also active. Or and the question is, what was the data that you used here? What do you display here actually?
I think it's in the paper it's written. I think it's the protein with the most ligands. So it's probably maybe it's ALDH1, I suspect, but in the paper it's written, if you want to be sure. So this is a graphical abstract image. So I guess there is a legend for it in the paper, and I say which target it is.